Vibration under general forcing conditions. The vibration response of a single degree of freedom system under arbitrary forcing circumstances is the focus of this chapter. The system's reaction to a general periodic force is depicted by first extending the periodic force into a sequence of harmonic forces using the Fourier series, and then superposing the responses owing to the individual harmonic forces. The system's reaction to a non-periodic forces is shown using two methods: convolution integral and Laplace transform. The impulsive response function of a system is used to convolution technique or Duhamel integral. The approach may use to be determined the response to base excitation. Several instances are provided. Demonstrate its use. The notion of response spectra corresponding to distinct forcing function, and their application in determining the system's maximum response is also discussed. The response spectrum associated with the base excitation, such as the individual by an possibility of a earthquake. Learning objectives. After completing this chapter, you should be able to do the following. Find the responses of single degree of freedom system subjected to a general periodic forces using Fourier series. Use the method of convolution of Duhamel integral to solve vibration problems of systems subjected to arbitrary force. Find the response of systems subject to earthquake using response spectra. Solve and damped system subjected to arbitrary force including impulse, step, and ramp forces using Laplace form. Understand the characteristic of transient response such as a peak time, overshoot, settling time, rise time, and decay time, and procedures for their estimation. Apply numerical method to solve vibration problems of systems subjected to forces that described numerically. This is the first order system and the second order system. Vibration under general forcing condition refers to the behavior and characteristics of a mechanical system when it's subjected to external force or excitations. These excitations can be various types, such as harmonic, random, or transient forces that can occur in multiple directions. When a system experiences general forcing conditions, its response is influenced by factors such as frequency, amplitude, and pace of the applied forces. The response of the system can be described in terms of displacement, velocity, and acceleration, which are primary parameters used to analyze the vibration. In engineering and physics, the study of vibration under general forcing conditions is crucial for various applications. Understanding how a structure or mechanical system responds to different types of forcing help in designing and optimizing structures to withstand dynamic loads, predicting the behaviors of machine, and evaluating the potential of the resonance or instability. To analyze vibration under general forcing conditions, engineers and research using techniques such as modal analysis, frequency response analysis, and time domain analysis. Modal analysis involves determining the natural frequency and mode shape of a system, which are essential in understanding its dynamic behavior. Frequency response analysis helps in understanding how the system responds to different frequencies of excitation, while time domain analysis examines the system's response over time. Overall, the study of vibration under general forcing condition is essential for understanding the dynamic behavior of mechanical system and structures and plays a crucial role in fields such as structural engineering, mechanical engineering, aerospace engineering, and many others. In a typical suspension system, there are various sources of external force or excitation can be lead to vibrations. These forces include road irregularities, vehicle speed, variation, braking, and cornering forces. Each of these forces can have different frequencies, amplitude, and pace, make it a general forcing condition scenario. When the vehicle encounters a bump on the road, it generates a transient force. The force is transmitted to the tires and suspension components, causing the vehicle's body to vibrate. The suspension system response to this general forcing condition can be analyzed to assess its performance and determine if any improvements or adjusts are necessary. To analyze vibration under general forcing condition, engineers will typically measure and record the response of the suspension system using sensors placed on various components such as shock absorbers, springs, and chassis. These measurements can include the displacement, velocity, and acceleration of the system at different locations. By analyzing the record data, engineers can determine the system naturally, frequencies, mode shapes, and damping characteristics. They can also evaluate the frequency response of the suspension system to different types of excitation. This information helps in optimizing the suspension design to provide better ride comfort, stability, and control. By studying the vibration under general forcing condition in a suspension system, engineers can design vehicles that offers a smooth ride, better handling, and improved safety. This example illustrates how analyzing vibration in a specific application helps in understanding the dynamics behavior of mechanical system and enable engineers to make informed design choices.